A todos, quisiera daros la bienvenida en nombre del Donostia International Physics Center, del DIPC, y agradeceros una vez más a todos vosotros por estar aquí. Hoy vamos a escuchar una conferencia titulada Física y Ficción, viaje a través del alma de los físicos teóricos, impartida por nuestro invitado, el profesor Giovanni Vignale. Giovanni Vignale es actualmente profesor de la Universidad de Missouri, en Columbia, en Estados Unidos. Tras graduarse en la Escuela Normal Superior en Pisa en 1979 y doctorarse en la Northwestern University en 1984, realizó estancias postdoctorales en el Max Planck Institute en Stuttgart, en Alemania, y en el Oak Ridge National Laboratory en Tennessee, Estados Unidos. En 1988 se incorporó al Departamento de Física de la Universidad de Missouri y fue elegido Fellow de la American Physical Society en 1997. Ha sido investigador visitante en el Centro Internacional de Física Teórica de Trieste, en Italia, en la Escuela Normale Superiore en Pisa, en el Instituto de Física Teórica de Santa Bárbara y también aquí en San Sebastián como Basque Fellow. Sus temas de investigación se centran en torno a la teoría de muchos cuerpos en materiales y dispositivos electrónicos. Es además autor de los libros Quantum Theory of the Electron Liquid y The Beautiful Invisible, Imagination, Creativity and Theoretical Physics, en el cual está basada esta presentación de hoy. Giovanni, please.
Okay, so thank you very much. I'm really very happy to be here, and thank you for taking time and coming here to listen to this talk. I'll try to make it interesting and entertaining. And you see, the reason for this title, Physics and Fiction, is in part because I realized that, although physics is really responsible for great advances in technology, for example, most people are not really so attracted by the technological applications. They are more interested in the fundamental, in the humanistic component of the science. And so I thought that it might be interesting to look at physics from a little bit of a different perspective. And let me tell you right away that at first sight, this seems a little bit like a stretched comparison, because in general, fiction does not very much care about the strict laws of physics. In fact, there is a particular brand of literature, a marvelous literary style, which is called magic realism, which is just based on the idea that you have to violate the physical laws, you have to suspend them, you have to have miracles happen, impossibilities, and so on. Now, this picture that you see here is an example, is an artist's conception of an episode from a novel that makes use of magic realism. The novel is The Master and Margarita, a great novel by a Russian novelist, Mikhail Bulgakov. And so the novel, in this novel, the devil himself, Satan, comes to Moscow in the middle of the 1920s. And he comes with several collaborators, like a black cat, whom you can see there, and also a clown, a vampire, and so on. And his arrival starts a lot of tragicomic episodes. But here is one of my favorites. So here you see that finally the police, the cops, have just managed to surround the cat Behemoth, and they're shooting at him, and cat Behemoth is shooting back. But strangely enough and surprisingly, nothing happens. The bullets have lost their ability to wound, to kill. They just pass through the bodies. They are dematerialized. So you have here a complete suspension of the laws of physics. And you might say, well, this is an absurdity because, of course, it cannot happen. And so, but within the novel, within the magic realism of the novel, is just perfect because it preludes, it prepares the dissolution of the material world, which is the theme of the very end of the novel. Okay, so having said this, nevertheless, I can show you now something that, and I hope this works, okay? That it's somewhat different. That is, I will not, you know, not all fiction, right, is like magic realism. So there is, for example, there is science fiction, right? In science fiction, the writers try to use science in their story line, okay? But I'm not going to talk about that. There is also physics written by physicists or by ex-physicists, and I will spare you that, okay? But what I want to show you instead is that there is some fiction inside, within the structure of physics, okay? That physics needs fiction to express its concepts. And for this, I start with this somewhat provocative statement by a famous psychoanalyst, French psychoanalyst Lacan, that the truth has the structure of a fiction. So although ultimately in science we try to establish certain truths, these truths must be formulated and explained through a metaphorical and fictional language. And here, look at this. Well, I hope you can look at this. Okay, so here you also have a striking violation of physical laws. You see, I think you will recognize here Jesus Christ walking on the waters, okay? And this is not just magic realism, although it might be mistaken for. It's just the Gospels, okay? To some people, this is the absolute truth, okay? And so is this truth or fiction, right? So depends, the answer probably depends on what you believe, what your faith is, and so. I personally would say that obviously it is both, okay? You know, there is a fiction in the sense that most likely Jesus did not literally walk on the water, but there is truth in the metaphoric meaning of the situation. So telling you that faith keeps you afloat when things become rough, okay? Just to simplify the thing. Okay, so this technique to express truth through metaphors and fictions, and so it's very well known in contexts which have nothing to do with science. And so it is not surprising that scientists also adopt similar techniques, okay? So, for example, I want to show you here, more or less in a random order, a series of myths that are created by physics. Okay, so here are just some, okay? It is not an exhaustive list by any means. The Big Bang, okay? So everybody has heard of Big Bang cosmology. You know, we like to think that the universe started with a dramatic event, very well localized in space and time. This is one of those things that, one of those ideas that exert a great attraction on human mind. But of course, you know, you all realize that such an event is, by its very nature, is beyond the possibility of direct observation. You know, it's even less observable than Jesus walking on water. At least he had some disciples who could witness in principle. Now, this cannot be observed, although, of course, there is some indirect evidence that fits with the idea, something like the cosmic background radiation, you know, in premise. Okay, so by the way, if you want to see a beautiful rendering of this idea of the Big Bang, you know, imagine that there were already people at the time, so just read the Cosmic Comics by Italo Calvino, which does a superb job of imagining the Big Bang in very human terms, okay? The title of that story is All at One Point, okay? Now, but then, you know, consider the second one, inflation. This is, you know, a relatively less popular idea, but it's a very interesting idea. It's the idea that there was a stage in the evolution of the universe during which the size of the universe increased exponentially, very rapidly, for an extremely short period of time. Okay, so it's so short that I cannot even begin to tell you how short it is. It's billions and billions of times shorter than the shortest thing on which we have ever done any experiment, okay? So clearly beyond any possibility of direct experimental observation, okay? Nevertheless, you know, physicists assume that this happened, and this is an extremely interesting idea because it introduces perhaps for the first time a kind of evolutionary element in cosmology. Like, things can really change in time. There can be different regimes, different eras, like in the evolution of a planet, for example. So, okay, so then, but let's come to more mundane things. The spin of the electron. This is something that we all have heard of. The electron is a relatively familiar particle. It's very important for technology. The spin of the electron is very important. What is the spin? Is this idea that the electron is, in fact, spinning around its own axis like a top, okay? Now, this is, of course, complete nonsense, okay? There is the electron, if you consider it as a particle, is a point particle, has no body, okay? It's just a point, has no body to turn around, okay? You can see that you run into all kinds of contradiction if you literally believe that this particle is spinning, okay? But there is a property of the electron that is formally equivalent to a rotation. And for this reason, we say the electron has a spin. It's just a metaphorical way of speaking. And coming to talk of the electron, you can also say, well, most of you, I guess, think of the electron as a particle, but is it really a particle? Actually, no. The answer is, initially maybe it was thought of as a particle when it was first discovered at the end of the 19th century. But later, with the advent of quantum mechanics and beyond, it became clear that the more fundamental thing is a field. There is an electronic field that extends all over the universe, and that occasionally, here and there, it manifests itself as an electronic particle. So the particles, they sort of exist on a certain scale, if you observe things, not too closely, let's say. But they cease to exist whenever you probe too deeply into the nature of things. And then, of course, we have this imaginary geography, this mythical geography of the black holes, this thing in which you, like Dante's Inferno, right? You go in, but you can never get out. These have, although there is indirect evidence, again, for black holes, but they have an essentially mythical character. And in the end, when everything else fails, if there is something that you really don't know what it is, like now it seems that there is a lot of matter unaccounted for in the universe, then you just call it dark matter, another mythological construction that basically covers it all. Now, the point I want to make here is that this stuff is really, so you might think, okay, so these are things that are said just for the sake of expressing, explaining things to non-specialists, right, to popularize the subject, but this is not so. I mean, this language, this metaphorical language, is really an essential part of the way we think about the science itself. And I should say that all these things are taken very, very seriously, okay? So, for example, just a few months ago, there was a very important discovery of certain gravitational waves affecting the polarization of the background, or the cosmic background radiation, which in fact is believed to be evidence for the inflation. So Nobel Prizes are given, okay, on these things, even though they can never be, directly observed. Okay, so, however, and this is a very important point, you shouldn't think that it is easy to come up with myths, okay? And this point was made very beautifully by the great Argentinian writer, Borges. So you see, I have something in Spanish here, finally, the Manual de Zoologia Fantástica. This guy, Jorge Luis Borges, he wrote this book, which basically is a collection of imaginary animals, such as the unicorn. There are a few more, several more. But he points out, and this is a very interesting observation, that the number of imaginary animals is actually much more limited, much smaller than the number of real animals. The fantastic zoology is much more limited than the real zoology. And why? Because, in order to become a mythical animal, it has to have a special power of attraction, okay, for the human mind. And the same thing, I would say, happens in physics. There are certain ideas that keep coming up in our way of thinking. They never go away, like particle fields vortices, strings, sudden explosions. Okay, there are, all kinds of, there are certain special, especially I call them charismatic ideas that come up. But generally, it is not easy to come up with something that really catches the imagination of a scientific community and therefore, becomes a real scientific myth. So, in addition, you see, there are lots of constraints in this construction of myths. Okay, there are internal constraints that come from the internal structure of the science, which the science physics is expressed in mathematical language, and so all these ideas must satisfy some internal mathematical consistency. Okay, cannot violate certain general principle requirements, like for example, the principle of relativity. Okay, is still believed to be true, right? That the theory should look the same in all reference frame. That is an internal constraint on any theory. Okay, there are of course external constraints, which means that your theory or myth has to be consistent with key experimental facts. Okay, it doesn't have to explain the details of everything that you see. That's impossible. Okay, that will never happen. But it must be, consistent with certain key qualitative aspects of the observations, and so you need a lot of precision in your fantasy. Okay, you cannot just imagine things and hope that they will work out. They must be articulated very precisely. For example, an idea which I think eventually will become articulated is that of an evolution of the universe, right? I believe that certain ancient myths of China postulate that the universe did not start in one day, but it slowly evolved, a little bit like life, okay? Now, that's an idea, a fascinating pattern that could definitely be developed, but you cannot just say, oh, the universe just took a long time to happen, but you have to find evidence. You have to find that it is consistent with everything else we know, and that's where the real challenge lies. At any rate, the point remains that because of this presence of all these constraints, the observations can always sort of unsettle your perception of things, and I like to say that better observations demand better myths. After all, even the Greeks had myths, right? I mean, that the sun was, a chariot led by horses of fire and so on. The observations probably were not so accurate then, okay? But better observations demand better myths, but no matter how many observations you make, the point that one must not forget is that ultimately the essential, and this is one of my themes around which I built my book, The Beautiful Invisible. The essential is invisible to the eye. That's the quotation by Saint-Exupéry. So observations provide constraints, but ultimately you have to make that leap, and in which you can only imagine the thing. Now, this, by the way, in case you have not recognized it, is a picture taken from Star Wars. It's Luke Skywalker trying to hit the target with a screen lowered in front of his eyes so that he cannot see, and he must just perceive, with some other sense, So in some way, theoretical physicists are a little bit like that, trying to hit the target without really seeing it, just imagining. Okay, so now what I said so far is very general. Now I would like to give you some a little more concrete examples, okay, of how these things work. In some examples. Okay, so let me begin. See, here I chose a deliberately provocative title for this slide. I would like to argue that compared to Aristotle, Galileo went beyond observation, right? Normally, Galileo is considered the founder of experimental science. So normally people would say, well, the guy who taught everybody else how to observe is Galileo, right? But it's not quite right, I think. So if you think about it, Aristotelian physics is actually very close to direct observation, and in fact almost based on direct observation, even though this observation is not very sophisticated, okay? Not, it doesn't have, sophisticated instruments. Aristotle basically thought that the Earth on which we live was a special place, a very special place, and I think that is true. I mean, it's very hard to deny that. Right? It was a special place, not a very good place. It was full of sin, as opposed to the beauty and purity of the heaven. And he observed things that are undoubtedly true. For example, solid objects within our reach, they tend to fall on the earth, right? They gravitate towards the earth as if they belong to the earth. Okay. On the other hand, flames and gases, they tend to rise as if they belong to the sky. So he observed that the motions on the Earth tend to occur on straight lines and then to end due to friction, right? Whereas the motions in the sky revolve forever on circles, okay? So he drew this sharp distinction between the Earth and the sky. On the Earth, you have rectilinear, straight motions. On the sky, you have circular motions, okay? All this was not absurd, right? It was more or less based on observation, okay? Now come Galileo, and he does something quite intriguing, maybe revolutionary, He makes, in some sense, a leap of imagination, and he has this, he writes that, if you have a ship here on the surface of the Earth, and if you give it a push in one direction, the ship will begin to just go around without stopping, in a circular motion, if nothing else intervenes, if there are no other disturbances or things like those, okay? Now, of course, Galileo has not done the experiment, right? Because he cannot do it. It's impossible to do this experiment, right? Period. But, there is something very new here. You see, there is a circular motion taking place on the Earth, an infinite, closed, perfect circular motion. The Earth is not supposed to allow for such perfection, okay? But Galileo says, no, if you let it alone, it will happen. Now, this is a big step. But you see, in some sense, he's still working within the Aristotelian framework because he doesn't want to allow the ship to leave the Earth. And so he misses, by a little bit, but he narrowly misses the exact formulation of the principle of inertia, which in fact states, as formulated later by Newton, that this thing will in fact not go around in a circle, but it will go on a straight line forever, you see, to infinity. This funny symbol here, infinity, means something that we don't really know what it is. There is somehow an infinite space out there, which is beyond the vision of Aristotle, and apparently even beyond the vision of Galileo in this. Okay, so Newton was the first one who formally stated the law of inertia, and he created this myth of infinite space, which, by the way, I'm sure that sooner or later is going to be revised. Okay, but so one could describe what he does like this, because this is a little bit of a pattern. Okay, so here is the world. All that is the case is something that we really don't know what it is. Okay, it's a complicated thing. But then, on the world, there is a little spot of clarity, There is a little spot where people like Galileo and Newton and so do experiments, and they think about things, and they figure out things. Now, as soon as they begin to understand something, they extrapolate what they have understood. They create a tangent plane here, which, you see, locally it makes contact with the world, but eventually it flies away. It has absolutely no contact anymore with the world. And on this plane, on this infinite plane, they start constructing their theoretical construction. So here it comes, So this is Newtonian mechanics with all its fancy laws. Newtonian mechanics lives in a really infinite space, which is the same in all directions. It's uniform, it's isotropic. It's a space that is obviously a mathematical abstraction. It's almost sure that the real cosmos in which we live does have a structure, and that is not true that all points are equivalent, I think. But from the point of view of deducing the laws of mechanics, that was the right thing to assume. Anyway, so this is the situation with, and you know, this is very effective because based on, the mechanics of Newton, you can send satellites to Jupiter and back, and you know, you can predict the motions of all planets with great accuracy, you know, and so on and so forth. But in a sense, this plane, this infinite space of Newton, is an imaginary entity. Okay. Now I want to come to a less appreciated thing, you know, the myth of continuous time. Okay, which is very pervasive. Okay, we all sort of feel that there is a continuity in time. Okay, so now this goes back. I mean, the first one to have doubts about, to pose the problem was a Greek philosopher, even before Aristotle, right? It's Zeno's paradox. You know, he formulated a very, very famous paradox, the paradox of the arrow, okay? And the paradox was this. We all know, we all believe that an arrow can go from point A to point B, right? We have seen it with our own eyes. But the point is, Zeno says, well, if I take a snapshot, I can imagine, right, this strip is a series of instantaneous pictures, snapshots, okay? I can take very good snapshots. He probably couldn't do that in his times, but he probably saw the possibility of doing it, you know? And in each of these snapshots, the thing is, the arrow is standing perfectly still in the picture. I don't see any motion in the picture, right? It's just standing still. So it occupies its own space, it stands still. So how can a thing move from A to B when actually it is standing still at each instant, okay? So, you know, it's a sort of, you know, you can see from our point of view, you know, we probably wouldn't even ask the question. And why we wouldn't? Because it's ingrained in us, the idea that in between the snapshots, there is a kind of continuous evolution, right? There is something that kept going on, even when we were not looking, okay? In between the snapshots, there was a continuous evolution. So we postulate a continuous time, and we define an instantaneous velocity through a very precise limiting procedure, you know, which involves a limit of the displacement divided by the time. So we can give a meaning to the velocity even when there is not yet a displacement, even when the thing is just there, okay? But, of course, and then, you know, this allows us to write what is called differential equations for the motion, okay? So what happens in practice is that one can summarize mechanics in this statement, okay? That there is a velocity and there is a position, and the velocity tells position how to change, and at the same time, the position tells the velocity how to change. So these two things evolve together like the double helix of theoretical physics, okay? And they promote the motion, okay? However, so this was all very fine, okay? So, but it's all based on this idea that time is continuous, right? And you can define velocity and positions simultaneously. And then comes quantum mechanics, and it says that, well, maybe, you know, Zeno was not completely wrong after all, you know? Because, you know, what happens in quantum mechanics? Now, quantum mechanics is the mechanics that holds at the very microscopic level. It holds for particles that are very light and very small, like electrons, atoms, and so on and so forth, okay? When you go to that level, it turns out, and this was basically discovered by people like Heisenberg, for example, with his uncertainty principle, that you can no longer define position and velocity simultaneously. So the concept of a continuous trajectory, you see that the red continuous trajectory that I had on the previous slide, it really falls apart. What you have now, you just have the Zeno's snapshots, and meaning observations. I observed the arrow first here, then here, then here, just like a particle passing through a cloud chamber and leaving spots at you know, discrete points. But then you don't really know. You cannot tell what happened in between, okay? But quantum mechanics does, in the end, recover continuity, the continuity of time, and it does it at the price of introducing a new invisible object. And this object is this magic-looking psi. It's called the wave function. the quantum mechanical wave function. It's a mathematical object, okay? It's a field, so it's a number that exists at all points in space. Not only is a number, but it's a complex number, okay? So complex means it has a real part and an imaginary part. It has to have two components because there is a position and there is a velocity. Okay, so the real part tells the imaginary part how to move. So the imaginary part tells the real part how to move. So it's really, what happens is that now there is still a continuous evolution, but the continuous evolution is no longer the evolution of the arrow. It's the evolution of this wave function, which smoothly goes on. And this wave function allows you to predict the probability of sighting the particle here and there. But this psi itself is like an oracle. You see, in case you didn't recognize this is the oracle of Delphi, the oracle of Apollo in Delphi, okay? So you ask the wave function a question, what is the probability of finding the arrow there? And the wave function allows you to calculate. So the person who has the wave function has a big advantage compared to the person who doesn't have the wave function, okay? But this wave function by itself is not an observable object. So it's another of these, mythical objects. Anyway, now I would like, because I don't think I have a whole lot of time, but I would like to give you another couple of examples that come closer to my field of expertise, that is the condensed matter. So I study systems composed of many, many particles, which quite often show organized behavior, okay? And one of the main manifestation of organized behavior is order, okay? So this is, for example, a snowflake, right? Made, there are these small crystals of ice all organized in a very symmetric pattern, okay? So this looks, first of all, it looks beautiful. Secondly, it looks like it's very symmetric. In reality, however, the symmetry of this thing is much less than the symmetry you should expect just on the basis of the pure physical laws, okay? Because the physical laws, remember Newton, what he said, the space is uniform, isotropic, is the same in all directions. The physical laws do not lean to the left or to the right or to the up or to the down, so they are the same in every, they have no preference. Okay, there is nothing in the physical laws that says that this point is better than that, and that therefore this should be occupied and that should be empty. So you see, the whole concept of creating an order structure means that you have to somehow reduce the symmetry of the original equations of the theory, right? So you have to find solutions of the equations which have less symmetry than the original laws, okay? So this is really a big problem because it turns out, at least in quantum mechanics, that if you do a serious theoretical calculation of the equilibrium state of any piece of matter, I mean, if you really are honest, you will find that there is no order because for every, so consider, this is a very, very simple case, okay? This is a molecule, is a molecule known as ammonia, It has 1 nitrogen and 3 oxygens, And it can exist either in this configuration with the nitrogen up or in that configuration with the nitrogen down. But if you do the quantum mechanical calculation, you will find a combination, a superposition of these two, And so you don't know, is it there or is it there, So in what sense can I say that the molecule is really this or that structure? Now, there is a much more dramatic way of rendering this. And at the macroscopic level, that's this idea that I'm sure you have heard of, the Schrödinger cat, okay? Of superimposing two things that are really, dramatically different, much more different than these two. In one, the cat is alive, and the cat is dead. But anyway, so the problem is that if you take literally the laws of physics, only the perfectly symmetric solutions are really stable. And any other solution will, so for example, if you start from this particular solution, it will oscillate back and forth you know, between this and that. So everything else that is not, so how do we understand the existence of order based on physical laws? Okay, so there is a trick to do that, okay? There is a mathematical procedure that is used. And by the way, here, rather than going into the mathematics, I chose to give you a little quote from an American transcendentalist philosopher, Ralph Waldo Emerson, is very, very well known, who I like particularly because it you know, shows in some sense the supremacy of the laws over facts, okay, in nature, okay? So this is a quote literally from Emerson: permanence is but a word of degree. I mean, in more everyday language, I would translate this as saying permanence is a matter of time scales, okay? So, and then he goes on saying, well, our world seen by God is just a law, not a mass of facts. And the law dissolves the facts and holds it fluid, okay? What does this sentence mean? This is how I interpret it, okay? So here is the point of view that we normally hold about ordered structure, okay? So what this is supposed to be is an ordered crystal with molecules in fixed positions, okay? Or it could be a government, a form of government, okay, that has been there for a long time. So the scale of time is finite. You know, this is, after all, the point of view of man, and we judge things on the scale of our own life, right? So we have a limited life to live. So our T is finite. N tends to infinity. N means that the crystal is very large, lots and lots and lots of particles, or that this is a very prestigious political system which has survived for many years, has many, many interests attached to it. You cannot control it. N tending to infinity, okay? And this is the point of view. And in this limit, order seems to exist, right? And it seems to be persistent. But then, if you interchange the order of limits, and that is the point of view of God, so all of a sudden, from the point of view of God, you know, there is infinite time because he lives or she lives in a sphere of eternity, okay? But every n is finite, okay? So no matter how impressive your government is, from the point of view of God, it will always be a pretty modest thing. Well, here is the fluid that Emerson is talking about. When you let the time go to infinity first, then that blurs your order structure. So you recover the symmetry of the physical laws. You lose track of order. So basically, the bottom line of this discussion is that order emerges only when you are on a finite time scale. But there is actually, strictly speaking, no order when you are on an infinite time scale. So if you reverse the order of these two things, okay? So order itself, in some sense, is a fiction, okay? It doesn't exist. All right, so let me conclude now with a couple of more you know, sociological considerations that I'm taking from my own field of research. At least this is a field in which I myself have done a lot of work. You know, it's called density functional theory, and I'm going to compare it to the quest for the Holy Grail, one of the great myths of the Western culture. Okay, so you know, the story goes more or less like this. Okay, so in the early 60s, there were these two guys, Hohenberg and Kohn. They proved a very important theorem. It's a theorem of quantum mechanics, according to which, you know, you can show that all the physical properties of a very complicated quantum mechanical system, you know, a piece of complicated matter, and so ultimately they are completely determined by the density of particles in the ground state. Okay, so you see there are all these particles flying around, you know, and somewhere they are more dense on the average and somewhere less dense. You know, at the borders of the system there are fewer and the center is more. So what they say is that if you know this distribution, okay, of particles, then in principle you know everything, in the sense that there is a prescription to start from that density and reconstruct everything else. Now, this, you have to appreciate that this is a very, very strong statement, because for the following reason. the density of particles is really a relatively simple object. It's a thing that we can almost visualize if we think about it, you know. You can almost imagine, okay, more density here, less density there. It's just a function of space, okay? But the properties of the system depend on that quantum mechanical wave function. Okay, now the quantum mechanical wave function is a function of the positions of all the particles in the system. So it's a function of millions and millions of variables. It's an object that it's practically impossible to visualize. Okay, so to say that somehow this simple density has enough information to reconstruct everything else is a really dramatic statement. And however, there is a catch, okay, that that is very difficult to extract that information. It's buried there in the density, but you can't pull it out. Okay, so what happens is that the essential information is encoded in a universal energy functional. Okay, it's called functional because it's something that you give a density and the functional produces a number. Okay, the energy that corresponds to that density. Okay. So there is this function which is uniformly applicable to all systems in chemistry, material science, etc. So the problem is, can we find this function? Okay, and here is where the myth comes. You know, I would say that the universal functional of density functional theory has in many ways a mythical status in the sense that it probably cannot be explicitly constructed. So the quest for that functional is a little bit like the quest for the Holy Grail that people, the knights of the Round Table were doing. However, and you know, this is a very important thing, the presence of this mythical functional has played an incredibly powerful role in focusing the research, the work of many, many research in the construction of better approximations for solving this type of problems, for solving many body problems. What I'm trying to say, and this, by the way, I forgot to mention that Kohn, at least, has won the Nobel Prize for Chemistry not too long ago, in 1998. You know, so why was this so important? You know, there were lots and lots of approximations that people were doing to treat this very complex system. Okay, but you know, none was charismatic. None could really capture the imaginations. They were all, you know, they look all like you know, different cooking recipes, okay? And now, all of a sudden, there is every approximation that you produce can be seen as a step towards that mythical functional that you are tending to. So this was a major step in energizing the research in this field. So this belongs more to the sociology, I would say, the way myths are used to catalyze the energy of groups of researchers. Okay, so I would like to conclude now with 3 points. Oops. Okay. So these are 3 points to remember. So the first one is that due to the presence of all these constraints, internal mathematical and external experiments, the physical theories are in some sense a kind of fiction, but a special type of fiction, okay? They're more similar to myths than just to stories, okay? So a myth is a very authoritative story that has taken a long time, has many authors usually, has been created by many people over an extended period of times, and is definitely more than just ordinary fiction. The second point I want to make is that the mythical character of the theory does not diminish its scientific validity, as someone might. In fact, quite the contrary, okay? Because to find convincing myths is not easy at all, okay? It's an art in itself. And they come with great effort, okay? So I would like also to add that better observations demand better myths. I'm pretty sure that pretty soon we will have to start addressing the issue of the non-uniformity of the universe, of the possibly of the existence of a privileged reference frame in the universe, and so on and so forth. And finally, I would like to emphasize that the mythical and metaphorical content of the theory is not something that we introduce just for the sake of popularizing, making them more easily accessible. They are just an essential part of the science itself. And finally, you know, I would like to say that physics does not explain really the world, okay? It just, you know, enables us to think about it, sometimes to predict some things. The ultimate nature of things is probably not accessible, I think, but definitely, you know, we can, you see, here I'm using this Robert Musil quote, which says, I am not interested in real explanation of real facts. Okay? Facts are interchangeable. I am interested in the spiritually typical. I could even say in the spectral dimensions of what happens. Okay, so in fact, this spectral dimension is what the theoretical physics is really all the time. Sorry, I mean, I think I did something wrong here. Okay, and this is my great picture, right, which shows this self-consistently. So a physical theory, you know, in some sense, is closed on itself because as far as possible, because it has to support its own empirical foundation. It has to be consistent with all this big mass of facts. Okay, and then at the top you have this nice, elegant architecture. And so the theory is supported by experiment, and the experiment supports the theory, and they just hang together as a closed, that might come down crashing any moment, but somehow it manages to levitate in the air. Okay, so if you want to know more about this way, this line of argument and so on, I've written many of these things in this book, you know, The Beautiful Invisible. And I thank you for your attention, and I'll try to answer some questions if I can, if they're not too difficult at least, okay? Thank you very much.
Bueno, ¿me escuchan? Sí. Bueno, primero que nada, muchísimas gracias por esta charla muy interesante y a la vez estimulante.
Do I have to wear this? Yeah. Okay.
Channel 2.
Yeah,
Okay.
I got that much.
Bueno, tenemos tiempo para preguntas o comentarios. Si alguien se anima a comenzar. Muy valientes, ahí hay uno. Vamos a esperar el micrófono, por favor, para que le puedan traducir la pregunta del ponente.
Speak in English.
As you wish.
Okay. So you say that you said that molecule. That molecule oscillates between these two states.
Right.
You already know me.
Yeah, I know.
So you would say that, I would say that if you would wait long enough, the Schrödinger cat would oscillate between death and being alive.
Yeah.
So you're kind of saying the afterlife myth, that everybody would stand up once again, and this theory would support if we all wait long enough. If there is a God who has infinite time, can see a time that everybody stands up and be alive again.
Yeah. Sure.
So all of these, so what's the difference between religion and...
Well, there are lots of differences.
No, I'm saying that what's the concrete difference, the consequences of these difference between religions and quantum mechanics?
Well, I'm not really, trying to draw a comparison here between religion and quantum mechanics, you know. But I'm just trying to say that the concept of order, right, of something being this way or that way, is always, limited to a certain choice of limits, right? So that eventually, when the time becomes long enough, if you have prepared the system in an exact superposition of those two states, it will keep oscillating exactly forever between those two. Now, the question that you can ask is why those states do not occur in nature, right? I mean, it's at least nobody has seen them. But in some simpler situations, they have been realized. So it is possible, with magnetic systems, actually, not with dead and live cats, of course. I mean, so there is definitely something that tends to destroy those superpositions, yeah, I mean, these are very, very complicated questions. I think we should talk about them in private if you really want to go deeper there. So.
Una pregunta por aquí. Bueno, te doy.
Thanks a lot for this very engaging talk. And I was wondering, you're using the word metaphor, the word myth, I think in a similar way to what some other people might use the word metaphor or the word analogy, right? Mm-hmm. And if I well understood, you're talking about some analogies or some myths that may be kind of new myths that trigger scientific research towards a particular direction. But earlier in your talk, you talked about these, what do you call these myths that come up again and again, these structures that are kind of recurrent and appearing all the time, again and again, which rather than new myths seem to be some things or some elements of these myths which keep appearing again and again. I wonder if you could say more about that, about this kind of dual sense of the word myth that you're using, which is this kind of new thing that triggers new research, but at the same time, something that kind of keeps present again and again, popping up somehow in scientific creativity.
Yeah, so you were thinking, for example, the last example I gave of the myth of the functional, right, versus, for example, a myth like infinite space or the point particles or so. Yeah, okay, so clearly I would say not all of these myths have the same status, right? And some are definitely more recent and contingent. They might go away eventually, It's quite possible, for example, in that particular example, that this myth of the universal functional might eventually go away if it is found that there is a better and more efficient approach. So right now, people are trying very hard to use that approach to solve problems. But eventually, at some point, they might change their mind and decide that it's just too difficult and start using a different method. Now, on the other hand, there are there are myths that are really extremely resistant, and keep going. Now, one of the most spectacular in this sense is this idea of the ether, right? This so it really keeps coming back essentially. Even so, when I was a kid, of course, I read about general relativity, Einstein's relativity, and I concluded that this ether that no one can observe, but it supports light, must be some kind of medieval superstition. But right now, it's coming back in the context of modern cosmology as provided, as the reference frame of the background radiation, basically. So, and there are many other examples. So light, for example, initially was a particle in Newton's view, right? Then it became a wave. Then it came back to particle with Einstein. So you see, there is this perpetual oscillation, that goes back and forth between different. So I agree. I don't think that this myth I was describing to you of that the universal function has the same status as those other ones. They're definitely in a different league.
¿Más preguntas o comentarios? Sí.
Thank you for your very interesting talk. After listening to your discussion, I'm wondering whether there is I mean, science, in my opinion, is something, it's not just pure description, because we can do predictions with science, right? I think that's what makes science science. So thinking about, after your talk, I was saying, okay, maybe do we have predictivity without a myth or not? What's your opinion about it?
Do we have predictivity without?
Can we do predictions without having a myth behind or not?
Well, you know, it's all about predictions, okay? So ultimately, the usefulness of the myth, let's say the wave function, is precisely that it allows you to do predictions,
exactly.
right?
Otherwise,
no one would take it seriously, okay? So what I'm saying is that you need a paradigm, you know, that allows you to, you know, interpret, you know, to set up a problem, ask a question, get an answer, and then possibly see if you got it right or not.
So that's basically science, right? We need
That in that sense, but what I'm trying to say is that the paradigm is not really is not you know, a reproduction of the objective reality, right?
Sure.
It can be quite far off, and it is not even particularly important in some sense, because one can never reach a final answer on that, whether it is really the objective reality, whatever that is. So in this sense, my position is a little skeptical, okay? I would say. I don't believe that we can ever really know what is really out there.
Thank you.
I have a comment concerning to this last question. We can consider that science is a fiction that is able to make predictions in some way, according to your point of view.
Yeah.
I mean, the fiction which is able to make predictions, we call that science in some way.
Yeah, that definitely was the point of view, for example, of the founders of quantum mechanics, right? They realized that they were going away from, you know, a natural, intuitive, objective description of things, but at the same time, they were creating a tool that allowed to make predictions. So you see, you don't know what's going on in between two observations, you know, in the picture of the arrow, right? That there is that area in between. I mean, or in some sense you know it, so you know that there is a wave function evolving, right? But then that wave function is used to predict the probability of something else, which has nothing to do with the wave function. You see, it's just a tool for getting some useful information. Yeah.
¿Más preguntas o comentarios?
Yeah, there's another.
Sorry, I don't want to monopolize the thing.
No,
Let me ask another question, please. You're talking about myths like particles or waves or ether and all these things. You haven't mentioned much about mathematics.
Yeah.
Maths are intrinsically precise, right?
Yeah.
Whereas myths are analogous. I mean, they can have many interpretations and so on.
Yeah.
So I have two questions regarding the relationship between your myths and maths, right? One is, okay, what kind of relation there is between myths and maths? And the other thing is going back to the thing I was asking earlier about these kind of permanent structures that keep popping up again and again. These seem to be very much present in mathematics.
Yes.
So, okay, I was wondering if you could elaborate on that a bit.
Yeah. Mathematics, of course, plays a very big role. In fact, I would say that that's probably the biggest difference between the literary myth and the scientific myth, right? So the scientific myth has usually an underpinning in the. So this is what I tried to say very quickly when I talked of internal constraints. It's true that you know, these mathematical patterns are an extremely strong guidance in the construction of the theories. You know, so some things that have been done would have been impossible without the guidance of the mathematics, right? So for example, things like well, I don't want him to mention the Maxwell's equation because those, you know, he probably had still a more, you know, less mathematical way. But think, for example, the work of Dirac, you know, on the combination. So Dirac is a scientist who basically brought together the theory of relativity and quantum mechanics, and so he, you know, he realized that right, that the quantum mechanics of Heisenberg and Schrödinger was not consistent with the principle of relativity, and then just following that idea, how to make it consistent, right? So if you say, let's say the wave function is the myth, okay, but the myth has to be made consistent with the principle of relativity. Now, there is some real mathematics, some beautiful mathematics, so it's a very difficult problem to solve, okay? And the way Dirac solved was to realize that he could do it if he expanded, he gave more structure to the wave function. Instead of having just that complex number that I talked about, it also had to have internal components. And when you do that, it becomes, you know, amazingly possible to satisfy. But in the process, you also predict new things. It's like, you know, all of a sudden you predict antiparticles, right? And as a byproduct, you predict that the particle, strictly speaking, does not exist. Because the moment you try to localize it, you start generating particles. So I would say, I don't know if I'm really answering your question, but I'm certainly, what I'm trying to say here is that in physics, you know, more than in any other science, mathematics plays a huge role in shaping the form of the myth. You know, and I think that, for example, this inflation thing that I've been talking about very cavalierly, for example, it does really correspond to a mathematical structure, at least as far as an assumption on the geometry of space-time. Then what principles of physics are really at work in the inflation, I frankly, personally don't understand, and I'm not sure that it is generally understood at this moment, okay? But yes, so the mathematics is, you know, what I mean when I write fantastic precision, you know, I mean that, you know, a combination of, you know, artistic imagination and mathematical rigor, you know. So.
¿Alguna pregunta más? Well, I have one more, maybe the last one. You said at the beginning of your talk that Lacan said that the truth has the structure of fiction, and he was in some way separating truth from fiction. I wonder what is the vision today, if truth is a special case of fiction, or if it is a fiction which satisfies certain conditions, or...
Look, Lacan has a very well-deserved reputation for obscurity. I'm not sure, you know, his most famous statement is that the unconscious is structured as language, right? That's probably the most... In this case of the statement that the truth has the structure of fiction, the way I read it is that, after all, the truth is something that we construct, right? With, of course, not arbitrarily, you know, based on our history, our background, our observation. So, but in the end, it is something that emerges from, you know, debate, from criticism, from sometimes fights, you know, who is stronger. So in the end, is a product of the human mind, and in that sense, it is an artifact. So I think that's where the fiction element comes in. You know, it's something that you make up. Ultimately, it's always a made-up thing, okay, even when it is supported by many facts. So it's a kind of error that you cannot confute.
Bueno, si no hay más preguntas, nada, agradecemos otra vez la charla a nuestro invitado.
Okay, thank you. Thank you.